Good morning, chemists. There is a little bit of background information that we need before we can begin talking about balancing chemical equations, and I'm going to give you that information now about ionic compounds. Ionic compounds aren't as relevant in nutrition other than the micronutrients that we need, the calcium and the potassium and the sodium. So calcium and potassium and sodium are super important, and we'll learn about other micronutrients as well later in the quarter. But before we can talk about chemical reactions, we have to actually understand how to write down formulas for ionic compounds. So basically, we talked a little bit about covalent compounds. So I'm hoping that that's something that's pretty standard and pretty okay with everybody. This is when we bond two nonmetals together, and that they share electrons. And we said they can share equally and have basically a non-polar bond, right? And they can share unequally and they can have a polar bond. So when we talk about ionic compounds, what we're talking about now is we're talking about when a metal and a non-metal bind together. Okay, so we are actually going to talk about electrons being transferred rather than shared. So the difference, the one that makes it different, is sharing electrons between two non-metals and electron transfer between a metal and a non-metal. Again, these particles aren't as relevant. They're not part of the big macronutrients. They are kind of on the periphery of nutrition and biology, but they are fairly important for us to understand how equations can be balanced. Okay, so just basically talking about a review, we can identify ionic versus covalent if we just locate them on the periodic table. A hydrocarbon, a carbon and a hydrogen, is going to be a covalent compound because it's carbon and hydrogen. That chlorine and bromine is going to be a covalent compound because those are two, chlorine and bromine, those are two nonmetals. They're all halogens. The only ionic compound we have on here is going to be this copper. There's copper that's right here, combining with the oxygen right there. So we have a metal, remember, this is our division of metals over here and nonmetals over here. So we can actually tell just by looking at where they're located on the periodic table, how they're going to come together. And so we have one example of a ionic compound in here, and the rest are covalent. So before I move from this page, I'm going to give you a copy of this periodic table. And this periodic table is kind of cool. You can actually see that division, the line that I just highlighted right here, of our metals on this side and our nonmetals on the other. You'll notice that these guys, there's a pattern here. All the guys on this side of the periodic table all have a positive charge. We're going to call those cations in a second. And all of these elements on the other side of the periodic table are nonmetals, are going to be anions, negative ions. We'll call that in a second as we talk about that. So we understand this octet idea, this idea that everything's trying to achieve stability, and these atoms are doing it by losing electrons if they're metals and gaining electrons if they're nonmetals. So we're going to go into that right now. We'll kind of go through, again, the same question about how do we decide if it's an ionic or a covalent bond. Again, any carbon-hydrogen bond is going to be covalent. Hydrogen and oxygen, there's a water molecule, right? So that's going to be covalent. Magnesium and bromine, again, just noting where they are on the periodic table. Sodium is a metal. Let's do that in a different color. Sodium is a metal and magnesium is a metal. And then sulfur is over there on the non-metal side. And if you're not familiar with that, here's sulfur right here. And then when we look at the other particle, bromine, right there, we see it's also a non-metal. So this is going to be an ionic compound, and so is this one, metal with a non-metal. Basically, we can say that it's a left side of the periodic table combined with something on the right side of the periodic table. And that's kind of where we're going to go with this. Okay. So when we say the word ion, basically we're saying charged particle. Okay. The ones, again, that you're going to run into the most are things like sodium, things like potassium, And then things like phosphate, and I'll just put that on there just because we're going to talk about a polyatomic ion. So an ion is basically a charged particle, and that basically means that the protons are not equal to the electrons, because an atom is neutral, and the reason an atom is neutral is because the protons are equal to the electrons, and that's what makes it an atom. A cation is a positive ion, okay, and we've talked about those are the metals, okay, they are on the left side of the periodic table. And they have lost electrons. And that means that they have more protons than electrons. They have lost electrons. Potassium, calcium, sodium are all good examples of cations that you're going to run into. So then you can maybe understand that an anion is going to be a negative ion, that it's going to be a non-metal, and it's going to be on the right side of the periodic table. And it has gained electrons, and so it has more electrons than protons. And again, the whole idea behind what these guys are doing is they are trying to achieve stability, and they're doing it by gaining electrons or losing electrons. When we write the symbol, all right, oxygen is one of the ones that's really important. Chlorine is really important. And OH minus is really important. So those are that's another polyatomic. Okay. So when we look at the symbol, so what you'll notice is for the symbol, I'm putting the element, the sort of calcium is the element we're talking about, right? And then I'm putting up here as a superscript the charge, right? So it can be positive or negative, but that's sort of our symbol for that. Okay. So when we look at practice here, the ion symbol for an atom, I'll do one of these and I'm going to have you guys practice the other ones. So basically, if I remember my subatomic particles, remember my protons, my electrons, and my neutrons, we remember that protons give us the identity of the ion. So if I have 22 protons in this substance, I know it's element number 22. So I'm going to go to my periodic table and I'm going to look for element 22. Whoops. Where am I? Okay. So I'm looking for element number 22. And that element is number 22. Is titanium right there. Okay. So I'm looking at that element right there. Titanium. And so I'm going to put the symbol for titanium in there. And then when I look at 22 protons and 20 electrons, this is kind of like when you were adding integers together, this would be a +2 charge. And so that's what I'm going to write up here, titanium +2. I will let you practice the rest of those, and I'll put the answers on that when I upload this content to Canvas. I want to go down here and look at these where it's basically giving you, it's giving you some information, and it's asking you to give the symbol just like before, but in a different way. So when I look at barium, I know that barium is Ba, and when I look at it I gave you this chart here, when I look at barium, because it's in this alkaline earth metal family, it's just like all of these guys, they're all going to have a +2 charge. So when I go to write that ion, I kind of know that barium is +2. When I look at these elements with the Roman numerals on them, essentially what's going to happen with that is those elements are going to be in the middle of the periodic table. And some of them have multiple charges, you'll notice, right? And so what we do is we use a Roman numeral, and I'll get into that a little bit more, to tell you what the charge is on the ion. So for instance, if I look at iron 2, it's going to be Fe, because iron's symbol is Fe. And because it's a Roman numeral 2, it's a metal, it's +2. Oxide, we'll get into that, but basically the suffix oxide basically is telling you that it's an ion, and oxide ion is -2, and I'll get into that a little bit more. And then ferrous, I'll have you look that one up. There's ferric and there's ferrous, and basically those suffixes tell you what the charge is. So I'll give you that. Okay. What is the octet rule? Basically, the octet rule, I think we've spoken about, and I just want to make sure It is the fact that atoms bond to achieve what we call stability, okay, low energy, in other words, by getting 8 electrons in their valence shell. Okay, so we talked about valence electrons, and we talked about how you can look at the periodic table and you can tell how many valence electrons they have, right? We said this is 1, 2, 3, 4, 5, 6, 7, 8 when we talk about valence electrons. What is happening here is this is kind of explaining why things do what they do. All of these guys don't really react because they already have what we call an octet. They have a valence of 8. These guys right here, because they have 7 electrons, if we just kind of look at chlorine's valence, we know that basically by gaining 1 electron right there, it could have 8. And so you'll notice that when we think of the charges on the halogens, it's -1 for that reason. They all have 7 valence electrons and they want 8. And so basically they're going to gain 1 electron either by sharing or by gaining it from a metal that's giving it away. Okay. For the most part, if we think about the oxygen group, when we look at its electron structure, we know that it has 6 valence electrons, right? And if it gets 2 more, right, it's going to have an octet. And so you'll notice that for the most part, again, this is kind of non-metals and metals, but for the most part, as you think about these elements right here, they're all going to have a -2 charge. Nitrogen behaves the same way. With nitrogen, we know it has 5 valence electrons. We know that if it gains 3 more electrons, it becomes like an octet. It becomes like the noble gas in front of it. And so basically you'll notice that for this group, for the most part, it's -3. And so that's an explanation for how these charges are when you look at this sheet right here. So again, you'll have a copy of this. I'll bring it to you. These guys all have -1 because they all want 1 more electron to become like the noble gas to their right. And within reason, you can see again, there's that cutoff between metals and non-metals. These all gain 2 electrons to become like the noble gas to the right, and nitrogen group as well. You'll notice there's something weird about carbon and silicon and boron, and that's because losing 4 electrons is too much, and so they never make ions. They always share electrons. Okay, so over here, just talking about the other side of the periodic table, when we look at these guys right here, we said they're all +1. We didn't say that, but we are now. And that's because these guys all have 1 valence electron, and they're going to lose it to become like the noble gas behind them. So they're going to go back to the nearest noble gas. So lithium loses 1 electron to become like helium. Sodium loses 1 electron to become like neon, etc., etc. Again, that's how they achieve an octet. That's how they achieve stability. These guys all have 2 valence electrons, so they lose 2 electrons to become like the noble gas behind them. So +1 and +2. So basically, those are kind of the stable ones. Those are the ones that behave nicely. So -1, -2, -3, +1, +2 as far as charges go. So that's kind of a given. The rest of them have a little bit more of a convoluted story, but we'll get into that a little bit as we go through this conversation. Okay, so that answers this question right here. What noble gas electron configuration is each ion? So I'm going to go through a couple of these. We talked about, I'm going to go with aluminum +3. If you notice, when you look at aluminum on the chart, it's a +3, right? And that's because it's going to lose 1, 2, 3 electrons to become like neon. So when we ask that question that way, basically sodium is trying to become like neon. I'll let you play with the rest of these, and again, I'll get these answers up for you so you get a chance to practice those. Okay. Again, same question. I'm going to let you practice that. So just kind of reminding you, I know you probably know this, that positives and negatives attract, right? And that's what keeps the sodium ion and the chloride ion close together. When they transfer that electron, it's that positive and negative attraction. So this is what keeps ionic compounds together, this electrostatic charge. So we talked a little bit about this when we looked at that. Why do metals have positive charges? Why do nonmetals have negative charges? Related to their valence electrons. So I'm going to let you write that down and practice writing down what I just talked about. Okay, so let's talk about writing ionic compounds, and we'll take this further when we start to write chemical equations. But basically, first things first, I want you to understand what is an ionic compound. Why are the charges of metals positive? Why are the charges of nonmetals negative? Okay, so that's a big idea. So understanding that. Now we're going to get into writing compounds, and there's just some rules for this. It's not a huge deal. It's not too bad. Basically what you're trying to do is balance charges. So when we write ionic compounds like sodium chloride, right, this name is sodium chloride. You're familiar with this substance. Okay. Our rules are basically we want the charges to be neutral. Okay, and what that means is we bring the sodium together with chlorine. We have a +1 plus a -1, and that equals 0. Okay, this is also called charged balance. Okay, when we write the name, and this is where the "ide" part comes in, we write the name of the metal and we just leave it alone. So it's just sodium. And we take this atom of chlorine, right, off the periodic table. We change the suffix and we make it IDE. So this, so basically to name it, we're going to write the metal, we're going to write the non-metal second, and we're going to change the suffix to IDE. Okay, so basically when we take, so for instance, I'm going to write calcium chloride down here, all right, and I'm going to take calcium 2 plus. Again, you're looking at that on the periodic table. We know that calcium is an alkaline earth metal. There it is right there. We're going to put it together with chlorine right there. And so we have a -2 charge, or -1 charge. And so what we have to do is we have to make it neutral, okay? So we're making it neutral. We're making this particle neutral, which means I'm going to bring another chloride ion in. And my formula for calcium chloride is going to be CaCl2. Our subscript right there tells us how many chlorines we need in order to make this a neutral compound. We use the name of the metal and we change the ene, chlorine, to IDE. Okay, so another example would be if I took aluminum and combine it with oxygen. So I'm going to make aluminum oxide. Okay, so I'm going to keep the metal's name. I'm going to take oxygen and I'm going to change the suffix to IDE, aluminum oxide. And then, so this is our name. So we've named this. Okay, and we want the formula. And we want these to be balanced, right? And so here's where it gets a little bit mathy. We want to make these neutral. And so if I put aluminum together with oxygen right now, it would be a +1 charge because +3 and -2 are +1. But if I take a second aluminum, Al3+, and 2 more oxygens, right? If I have +6 and -6, I have a neutral compound. So I'm going to call that aluminum oxide. So it's Al2O3 in order to get a charge balance on that. Okay, so basically that's how that goes. And so what I tell students is when we write the formulas for ionic compounds, the first tier of this is just a metal with a non-metal, and it's kind of no frills, basically, okay? Essentially what we're doing there is we're balancing the charges, okay? We're balancing the charges, and we're naming it using these rules that we talked about down here, right? So you keep the name of the metal, you change the name of the non-metal to IDE and call it good. Okay, so there's lots of practice for this on this document, so I'm going to have you guys go with that. I'm going to pause and come back, and we're going to talk about 2 other ways to name ionic compounds.